Hello everybody, glad to see you. Today I'm going to continue to talk about the needed GD&T for shaft. Let me recap the needed GD&T for shaft as we have discussed last session. As we can see here at top left, for this end surface we need to use one of these three: flatness, let's say run out, or total run out, or perpendicularity. And whenever we are going to have, let's say, a threaded shaft, we need to use this positioning diameter symbol and this text as a major diameter. If we are going to have a threaded hole, as we can see here at bottom right, we need to use this positioning control, diameter symbol, and minimum diameter. And for other part of that, we are going to use run out and total run out. I haven't talked about the needed GD&T for key slot. I'm going to talk about this topic in coming sessions. And last item, as I would like to highlight it, is reference axis A and B. If you can remember it, at the beginning we have talked about that. We are going to have two bearings here, one here and another here, and we have this possibility, let's say, this surface as a contact surface between shaft and shaft coupling. I haven't chosen this bearing area as a reference axis A. I have chosen this one, this contact area. Why? Because it is contact area. It is very reasonable item to use this contact area for the reference axis. But another item is it is close to this end shaft. It is easier for machining. Based on machining, if it is close to end shaft, it is good idea to select that axis as a reference axis. And yeah, now we have recap everything regarding this needed GD&T for shaft. Here, in order to qualify our reference axis, we have used these tolerance sizes, this TZ for the size, to qualify that. And for the contact area between shaft and shaft coupling, as we have talked in, I guess, in session 5, we are going to have three different fittings. Let's say clearance, there is no interference between shaft and hole. And let's say transition fit, there is some interface between shaft and hole, and interference fit. In order to assemble, let's say, shaft inside the hole based on interference fit, we need to use some tools to hit or cool down and then do the assembly. And in that session, we have highlighted if you are going to have, let's say, clearance fit, if for shaft we are going to use H7, we have this possibility, as we can see at left hand side, we have these possibilities to use this, let's say, tolerances for the hole in order to have clearance fit. If you would like to have more information about that, please see session 5. The next item, as I would like to highlight, is balance quality grade. Let's say G as a grade based on this standard GIS B0905-1992. For different application, we are going to have different quality, different G. Let's say if it is flywheel, we need to use G6.3. Here, we are going to have this plot here. We are going to see several lines here. The horizontal axis is going to represent the velocity, the RPM, revolution per minute, and the vertical axis is going to represent E per. E per, as we can see here, is permitted, let's say, eccentricity. If we are going to multiply this E By mass, we can find permitted unbalance. What is the relation between permitted eccentricity and G? It is this relation. The balance quality grade G equal to E multiplied by omega. Here just I would like to say please take care about unit. If omega is radian per second, here in this axis we need to have revolution per minute. Easily we can convert it to n and then come with this graph and then see what is the grade of that shaft. It is G6.3, it is G2.5, and then we can find E, and if we are going to multiply E by omega, we can find this, let's say, balance quality. Let's see this example. In this example, we are going to have a speed of 9,500 RPM and the mass is 1 kilo. And for this application, the G is 2.5. We would like to see what is the value of the E, or let's say U, permitted unbalance, permitted eccentricity for E. Let me talk about this 9,000 RPM. Normally, this 9,000, 10,000, it is really fast, I can say. Between 10,000 RPM to 20,000, 25,000 RPM, it is really fast, I can say. In some CNC machines for finishing, we are going to have that higher speed. Between 6,000 to 10,000, I can say they are in the medium level. But in normal industrial application, the RPM is less than 6,000. However, for this example, it is 9,500. We can come here in this horizontal axis, let's say 10,000 here, and G is 2.5. I can come here, I can say yes, E is 2.5, 2.5 micrometer, and then I can multiply by omega and find G, or I can multiply by, if I'm going to multiply E by M, I can find, let's say, permitted unbalance. Regarding to this balance quality grade, we are going to have this quality for all rotating components. As we can see for the wheel in the car, we need to do that. For any rotating component in industry, we need to have this grade. As we know, we are going to have two balances, let's say a static balance and dynamic balance. And we can have more details in dynamic machine course. And for a static balance, we are going to use, let's say, single plane, and for dynamic balance, we are going to use two planes. Maybe in coming session in future, I'm going to talk about this balancing machine. What is the principle in that balancing machine? We are going to have different machines, and I'm going to a little bit talk about that in coming session. For now, I would like to close this session. In coming session, I'm going to continue talk about GD&T for this shaft coupling, and then I will go a little bit more detail about that, and then I'm going to talk about the second shaft, which is going to connect this shaft to another shaft with this shaft coupling. Thank you for today. I hope you enjoy it. See you next time.